In this video, we're going to walk through the solution to question number 2 from the problem-solving set that goes along with Chapter 9, the chapter on reactions of alkynes. And in this particular video, the question asks us to indicate the reagents necessary for carrying out each of the following conversions. So in other words, if we're trying to convert oct3-ine to a cis-oct3-ene product, what reagent or reagents would we need to use in order to carry that out? So to tackle a problem like this, I recommend that you first draw out the structure of the reactant and the structure of the product just to visualize things. So we need an 8-carbon chain here, oct3-ine. Gosh, who makes up these problems? I have to draw a really long carbon chain here. So we're going to draw oct3-ine. So we need an 8-carbon chain, and we need to have in that 8-carbon chain our carbon-carbon double bond between position 3 and 4, since we're calling this oct3-ine, or 3-octine. And then I went ahead and numbered my carbon atoms there. I'm going to erase that extra carbon that I had plugged in. And we're trying to convert this into cis-oct3-ene. So we have this alkene group at the same position of the chain that the alkyne group was to start with. And we want to make sure that we are drawing this as the cis configuration, the cis geometric isomer here. And I'm going to number my carbons out again to make sure that I've got the right number, because I'm usually 1 too high or 1 too low here. Let's need one more carbon atom. So we're showing the structures of oct3-ine as the starting material and cis-oct3-ene as our product. We've got that cis configuration there. So what we need to do here is we need to sort out how we can reduce the alkyne group to an alkene group. We call this a reduction reaction because we are increasing the number of carbon-hydrogen bonds. And when we increase the number of carbon-hydrogen bonds, that's going to correspond to a reduction reaction because we're lowering the number of carbon-carbon bonds, increasing the number of carbon-hydrogen bonds here. And we could also think of this as an addition reaction because we are adding hydrogens across this carbon-carbon triple bond to give the carbon-carbon double bond. So in order to do this, we have to think back to the ways that we are aware of for carrying out the addition of hydrogen across a carbon-carbon triple bond. So the ways that we've learned to add hydrogens to alkyne groups were we could do a simple hydrogenation with H2 and a metal catalyst such as platinum and palladium. The problem with that reaction is that it's very, very difficult to stop the addition reaction at the alkene. Instead, what generally happens is that the alkyne gets reduced to an alkene, and then a second addition reaction goes on to add another hydrogen to positions 3 and 4 here to reduce all the way to an alkane product with just carbon-carbon single bond. So I'm going to put the annotation here that using H2 and metal is going to reduce the carbon-carbon triple bond all the way to a carbon-carbon single bond of an alkane. So that's not going to be an appropriate way to go about doing the reduction that we're seeing here in part A. The second way that we are aware of for reducing an alkyne is that we can react the alkyne with H2, and rather than using a simple metal catalyst such as platinum or palladium, instead we use a special catalyst called Lindlar's Catalyst. And what Lindlar's Catalyst does is it poisons the reduction of an alkene to an alkane so that the reaction stops at an alkene product. It can't proceed onward to the alkane product. And so we can plug in here that this is going to reduce carbon-carbon triple bond of an alkyne to a double bond of an alkene. And when we think about the stereoselectivity of this reaction, it is going to give a syn addition. You could think of syn being that the two hydrogens are going to be adding cis to one another. They're going to be adding to the same face of the molecule. And so looking at the reaction that we are dealing with here in part A, I think we have a winner. So we are, by evaluating the relationship between the starting material and the product, what we see is happening here is that we are converting an alkyne into an alkene, and we're doing that so that the alkene product has the cis configuration there, and that would correspond to the syn addition. So therefore, the reagent that we need to plug in here is, if we use H2 and Lindlar's Catalyst, that's going to be the answer to this particular problem. So hydrogen and Lindlar's Catalyst are how you are going to convert alkyne starting material stereoselectively to an alkene product that corresponds to having syn addition, where we've added the two hydrogens to the same face of the molecule. Let's go on now to part B. And as we start into part B, I do want to add a third strategy here to our list of ways to add hydrogens to alkyne groups. And that is, if we use sodium metal, Na, and ammonia, NH3, the change that is going to affect is it's going to reduce the carbon-carbon triple bond of our alkyne group to an alkene, much like using H2 and Lindlar's Catalyst. The difference is that when you use sodium metal and ammonia, it's going to give anti-addition. Hence, the two hydrogens that are adding across the carbon-carbon triple bond are going to add to opposite faces of the molecule, one on top, one on bottom, you could think of it as, and that is going to lead to the product having the trans configuration. So it's preferentially going to yield the trans geometric isomer here. So let's go ahead and do part 2 here, and we'll try to match that up with one of these three strategies on the right that we've looked at for adding hydrogens across the carbon-carbon triple bond. So we're starting with pent2-ine. So we need to draw a 5-carbon chain, and at carbon number 2, we need to have an alkyne group going on there. So I have my 5-carbon chain, and we want to convert that to trans pent2-ene. So draw my 5-carbon chain in here, and at position 2, we need our alkene group. So we'll go ahead and do that. Now, at this point, we think about the relationship between our starting material and our product, and we ask, what is going on here? So what's going on here is we are adding hydrogens across the carbon-carbon triple bond to give an alkene, and we are doing that in a fashion that would be anti, because we are making the trans product. We're adding one hydrogen here facing upward, the other one facing downward here in the product. And so, consequently, the correct reagent to use here would have to be the sodium and the ammonia, because the other two possibilities would give either the wrong stereoselectivity to give the syn product, or if we just used H2 and metal, it would result in reduction all the way to the alkane product. So sodium and ammonia are the combination of reagents that we need to plug in here. So I'm just going to put sodium and ammonia as our two reagents for carrying out that reaction. So with this, we have used these problems as a way to review and highlight the three main ways that we learned for adding hydrogens across the alkyne group to give an alkane, or to give an alkene with syn addition, or alternatively, to give an alkene in a stereoselective reaction via anti-addition. These latter two reactions are both stereoselective, and the way that you would determine which of those to use to convert an alkyne into an alkene is you would keep in mind whether you wanted the reaction to give the cis product, meaning syn addition had taken place, or whether you wanted to give the trans product, meaning anti-addition had taken place. And that will allow you to determine what the best reagent is for your application. Stay tuned for the next video, where we will be going into more reactions of